This summer, I started volunteering with a group that puts on a yearly holiday light display known as Garden Delights at the Bellevue Botanical Garden in Bellevue, Washington. They do breathtaking displays of plants and animals, all made out of lights. This picture shows one of many displays. They had a problem. People didn't know what path to follow through the lights. They had made arrows out of LEDs, but they weren't distinctive enough. This is right in my wheelhouse. Here's the concept. We will define an arrow shape and space RGB LEDs evenly around the outline, and then do some sort of animation to make it eye-catching. And it was off to Fusion 360 to do the design. If you want the full details of how I did it, you can see in the linked video in the corner. The holes in corners are for mounting the arrow. The holes in the middle are attachment points for the control box, and they're on both the top and bottom so you can make both left and right arrows. The arrow will use what are known as WS2112 pixels. They look like holiday lights, but each light is an RGB LED, and the color of each LED can be controlled independently. They come in strings of 50 LEDs. Here's a proof of concept prototype in a piece of scrap melamine board I had lying around. It uses 25 LEDs. The feedback was, looks good, needs to be a lot bigger, which is why the design I showed you is bigger and uses 50 LEDs. Here's a setup for putting all the holes in the boards. I use a Shaper Origin, which is a handheld CNC router. It has an advanced vision system that uses what they call domino tape to construct a model where they can tell exactly where the router bit is. Since these will be out in the weather and it rains a lot here, I wanted a better substrate than plywood, so I used 1x8, actually 3/4 inch by 7¼ inch PVC trim board. It's expensive, but it will last forever and is also very easy to machine. Doing these made me really wish I had a conventional CNC, as it was 30 minutes for each board. All of that really boring. Even with podcasts, it was very tedious. White is the wrong color for a nighttime display, so they all got spray painted black. To make sure all the LEDs are at the same depth, I fabricated a little gauge block. If I recall correctly, it's 1 centimeter deep. In the upper right, you can see some of the pixels. The pixels are pushed into the board from the backside as far as they will go. Notice that they stick out too far and aren't even. Then we use the gauge tool to push them back so they are all the same height. Then the board is turned over and small blobs of hot glue are added on 2 sides of the pixel to hold them in. The pixels are nominally 12 millimeters in diameter, and I initially tried holes that were close to 12 millimeters for a snug fit, but there are little tabs to hold them in place, and those tabs mean it took a lot of force, and I risked damaging the pixels. I settled on 12.7 millimeters as a good size. It's a loose fit, and the glue holds them securely. If you're in the US and you want to do this by hand, you'll be happy to know that 12.7 millimeters is the same as 1/2 inch. So you can easily drill them by hand. The pixels come with 3 wire connectors, but I wanted something more robust and waterproof, so the 3 wire cable is soldered to the pixel wires, and each of them is covered in heat shrink. Then the wires are glued together, and a final outer cover of heat shrink is put over and filled with silicone, then heat shrunk after the silicone cures. The cutoff wires you see are also covered in silicone. On to the microcontrollers. I'm using an ESP8266 on the D1 mini board. The boards are numbered for reasons I'll talk about later. A few years ago, I spun some tiny boards for this exact scenario to make the wiring easier, and luckily I had a bunch left over. They connect to one side of the ESP board, and then have 3 pads for the pixel string connections, and 2 pads for the 5-volt power supply and ground. The power pads are connected to short USB power cables, which will be plugged into USB power supplies. Time to move on to the boxes. I needed 2 different sized holes for the 2 cables that will come into the box. They are drilled with a step drill, which is a great way to drill plastic. Normal twist drills can be very grabby in plastic, or even break it. Step drills avoided that. I also considered using the shaper to do this, but the drill press was simpler and easier. I drilled 1 hole and then set the depth stop so I could drill all 10 boxes with the same size hole. The box has small standoffs molded into it to make mounting boards more easy, but these take up space that I need for the contents. These are cut off with a Dremel and an abrasive wheel. Pro tip, you can also use a diamond wheel to cut plastic. It cuts more slowly, but is less melty. Here's the way the box finally looks. The holes are for what is known as a cable gland, which have a rubber insert that tightens around the cable and seals against water entry. Here's what they look like when installed. The maximum current for 50 pixels is 50 times 60 milliamperes, or 3 amps. That's for all pixels fully bright on white. The animation I chose generally uses only one channel full power, with some pixels at 2 channels, so the draw is less than 2 amps. I chose 2.4 amp 5 volt power supplies, and they're working fine. The AC prongs on the power supplies are too long to fit in the box, so I cut them off with the Dremel and an abrasive wheel. I held the prongs in my big vice grip pliers to keep the heat down. If you don't do this, the prongs will heat up and soften their mounting in the plastic and bend a little. The AC cord is made out of an extension cord, which tends to be cheaper than a power cord. It runs through the cable gland and is soldered to the AC pins on the power supply. Heat up the pins until they will accept solder, tin the wires on the AC cord, and then solder them together. This connection is then insulated with hot glue. And finally, tucked into the box and hot glued in place. After doing 9 of these, I realized that there wasn't enough room to plug in the USB power cable, so I had to cut the top bead of hot glue with my oscillating multi-tool, lever it up, plug in the cable, and then glue it back down. Not my finest moment, but mostly an annoyance. The smaller cable gland is for the cable that runs to the LEDs. The USB power cable and the LED cable get soldered to my tiny breakout board, and then the ESP8266 is just plugged into the header and then placed into the box. I somehow lost one of the 10 USB power supplies I bought, so I used this one for the last arrow. It worked fine for testing when it was plugged into the wall, but failed during the multiple day burn-in tests I did, probably from heat. Note that this box has a little waterproof gasket on the lid that will help keep water out. I also put packing tape on the top and sides of the box to cover the seam and keep water away from the gasket. On to the code. I think I've written 6 or 7 animation systems for various projects I've done. A couple years ago I wrote a full animation language called Fade. Follow the link if you're interested. I thought about using Fade, but it only runs on the ESP32 and, embarrassingly, doesn't easily support the kind of animation that I wanted. So it was back to hand coding. I started with some old code, tore out all the stuff I didn't need, and started very simply. The code is based on NeoPixel Bus by Makuna, which is my favorite solution for WS2112 LEDs on the ESP devices because it uses the hardware to send the data. The only downside is that it uses the RX pin to drive the LEDs, and that means when you update the ESP circuit, your LEDs all turn on to white. I also use the task library by Makuna, which has a very nice way to set up a chunk of code to be called periodically. In this case, it's every 10 milliseconds. All the code is in a GitHub library that is linked to in the video comments. Let's talk about the animation. We wanted something that was colorful, tasteful, eye-catching, but not too flashy. That meant smooth fades between colors. The animation is designed in a number of discrete steps, with a duration for each step. Step 1 goes from full blue to yellow. It needs to happen quickly, so the duration is 0.5. Step 2 sticks at yellow for 0.5, so that there is pure yellow for a noticeable time. Step 3 is the main blend from yellow to red, over a duration of 3.0. This is what people really see. Step 4 is a blend from red back to the default blue over a duration of 2.0. And finally, step 5 is a long hold at blue for a duration of 30. Once we have the color animation defined, we can apply it to the arrow shape using the same coordinate system. Here's what it will look like. The reason there is so much blue space is we want the animation to run, and then pause, and then run again. Here's what it looks like on the real arrow. And here's an animation. We essentially move the offset of the arrow's starting point along the color patch progressively. The abilities of PowerPoint continue to amaze me. The animation here is very close to the way the arrows look. There's one more issue to solve. In defining the colors, I use the full RGB values. 255, 255, and 0 for yellow, 255, 0, 0 for red, and 0, 0, 255 for blue. WS2112 LEDs are bright, and sometimes they're too bright. Easy enough to change in code. Just change the values and the LEDs get dimmer. But that means pulling the box down, opening it up, updating the software, resealing it, testing it. Not a lot of fun. So I added back some of the code that I had originally torn out of the project I based this on, and implemented a simple web server. The ESP in each arrow sets up its own wireless network with a unique name. In this case, Arrow 05. That's why the ESPs had numbers on them. You connect to this network with your phone, and then navigate to a web page. You can then change the brightness of the blue background color or the highlight colors of yellow and red. Those values are stored in non-volatile or permanent memory on the ESP, so that the arrow will always use those values. And finally, time for a video. RGB LEDs are notoriously hard to capture on camera because of their brightness. This video shows a typical result. You can see something going on, but the colors don't look very good. The arrow in the upper right corner has the power supply that is dying, so it isn't functional right now. I promise they look much cooler in person. Here's a close-up video I took with my DSLR. The brightness is turned down to make the colors more visible. But even with that, the color shows up mostly in the bloom around the LED, rather than the LED itself, which looks mostly white. Thanks for watching. I hope you found this project interesting.